Hello everyone. Today we'll see the solution of gas dynamics and propulsion questions of GATE 2011 paper. In GATE 2011, there were total around 12 questions from gas dynamics and propulsion, out of which around 5 questions were of 1 marks and 7 were of 2 marks. So we'll see the solution of all those questions in this video. The first question, for an impulsive launch of a rocket minimizes the loss of burnout velocity due to which of the following: aerodynamic drag force only, gravitational force only, both aerodynamic drag and gravitational force, or reaction jet control force. So for a impulsive rocket launching, the velocity increment, there is a formula for velocity increment, right? So that formula is as follows: velocity increment delta V is given by the following equation, right? So delta V is given as C dm by m, where C is the effective exhaust velocity, plus d by m dt plus g cos theta dt, right? Now for an impulsive rocket launching, let's just draw a schematic of that. So this is a schematic of rocket launching. This angle is theta. And this is exhaust velocity. And the mass coming out of the exhaust is dm. So for an impulsive rocket launching, the velocity increment is given by the following equation. Right now, if we consider this term as q, this term inside the bracket is q. So in the question, it is asked that the impulsive launch of a rocket minimizes the loss of burnout velocity. So the loss of burnout velocity, which is delta v, is minimized when q is minimized. Q is minimum, right? Now, if Tb is the burnout time, and for impulsive launching, Tb actually is reduced. For impulsive launching, Tb is reduced, right? And the velocity is higher. So this velocity is velocity of the rocket, this v. Now, if we see each of these terms inside of q, so if we see this term, the gravitational force term, so integration of g cos theta dt will give g cos theta tb, right? And hence the since the burnout time is reduced due to impulsive launching, so this term will reduce. So this term will decrease due to reduced TB. So hence this is hence the since this term is decreasing, so this term is a term which will contribute in minimizing Q, right? So this is one term. Now if we see the second term, this term, so d by m dt, this will give half. So d is the drag force acting on the rocket. So we know the formula of the drag force, which is half rho v square CD. And divided by m, and this dt can be written as ds by v, right? So this will give half rho by m cd integration of v ds. Now for an impulsive rocket launching, since for a given distance velocity is increased, so this term actually will increase for impulsive rocket launching. So this term will increase for impulsive rocket launching. Hence, this is not contributing to minimizing the burnout velocity, right? So our answer will be this term only, g cos theta dt. So gravitational force only will be the answer. Next question. The main objective of bypass in a turbofan engine is to increase the mass flow rate through engine inlet, mass flow rate through exhaust nozzle, turbine inlet temperature, compressor pressure ratio. Okay, so if we see the cross-sectional, so if we just draw a schematic of the cross-sectional view of a turbofan engine, this will be something as follows. So this is a schematic of half of the cross section, only the upper half of the cross section of a turbofan engine. Now this is a fan in the inlet of turbofan engine, I mean in front of the turbofan engine. And then this is the compressor. This is the combustion chamber. This is the turbine. And this is the exhaust nozzle. And in turbofan engine, there is another bypass nozzle, which is this one. And a percentage of the main mass flow rate which is being sucked by this fan is passed through this bypass nozzle. So this is the secondary nozzle or bypass nozzle. And this is the inlet velocity, UI. Now in gas turbine engine, the thrust, equation of thrust is given by T equal to m dot ue minus ui, right? Where m dot is the mass flow rate through the engine, and here of course we have ignored the fuel flow rate. So if he is less than 1, f is emf dot by ma dot. So basically ignoring the fuel flow rate. Right now, this is the expression of thrust in a gas turbine engine. Now, if we have to increase this thrust, to increase thrust, T, we have two options. So one option is either we have to increase exhaust velocity UE. So, but so for this case, when we have to increase exhaust velocity UE, for that case we have to increase the turbine inlet temperature. So to increase UE, we need to increase the turbine inlet temperature. Now, to increase turbine inlet temperature, we need to add more fuel inject more fuel in the combustion chamber. For that, more fuel has to be injected. And that actually reduces the thrust specific fuel consumption ratio. Thrust specific fuel consumption ratio also reduces the propulsive efficiency. Right. And hence this is not really economical. This option is not really economical, right? So if we have to increase, so one way of increasing this thrust is to increase the exhaust velocity. Now if you have to increase the exhaust velocity, we need to, like, the turbine inlet temperature has to be increased. So to increase the turbine inlet temperature, to inject more fuel in the combustion chamber, and which basically reduces the thrust specific fuel consumption ratio, which is not desirable, and also it reduces the propulsive efficiency of the engine, and hence this is not economical and not really suggested. So what is the other way? The other way of increasing the thrust is, the second method of increasing the thrust is to increase mass flow rate m dot, right? So if we have to increase T, one way is to increase UE, other way is to increase the m dot, right? So increase m dot or the mass flow rate, and this is the philosophy that a turbofan engine incorporates, that it increases the mass flow rate going inside the engine, and by that means it increases the thrust produced. So what happens in a turbofan engine? So, and this is the philosophy turbofan engine incorporates, right? Now in turbofan engine, what happens is that this fan of the engine, it sucks huge amount of air from the atmosphere, and a percentage of that air actually passes through the core engine, which is compressor, combustion chamber, turbine, and then the exhaust nozzle, and the other fraction of the air actually passes through this secondary nozzle, and this secondary nozzle accelerates that air, and it helps in producing more thrust. So this m dot, which is the mass flow rate of the air which is being sucked by the fan is actually summation of m dot core, the mass flow rate of the air which is passing through the core engine, and then the mass flow rate of the air which is passing through the bypass nozzle, right? So in turbofan, the thrust is actually being produced by both the nozzle. One is secondary nozzle, other is the exhaust nozzle. So for turbofan engine, the thrust produced by the engine is given by this. So this is the thrust produced by the core engine, and this is the extra thrust produced by the bypass nozzle. So the main purpose of this, the main objective of this uh, bypass in turbofan engine, or bypass in turbofan engine, is to increase the mass flow rate to exhaust nozzle, through exhaust nozzles, because this is the philosophy by which the turbofan engine increases the uh, thrust. Moving on to the next question. The pressure ratio in any stage, in one stage of a jet engine compressor is limited by which of the following: entry stagnation temperature in that stage, entry Mach number in that stage, pressure gradient induced separation in that stage, or mass flow rate in that stage, right? So if we just draw a schematic of a compressor, this will be as follows. So this is a schematic of a compressor. So I'm not drawing this is the blade. I'm not drawing the blades in the other side of the engine. So only one side I'm drawing. So this is the shaft which rotates, right? So this shaft rotates, and this are the rotor blade. This and this are the rotor blade, and these blades are the stator blade, right? So these blades does not rotate, this remains stationary. Now, and one rotor and one stator comprises one stage. One stage of the compressor, right? Now, as the flow passes through the compressor, the pressure increases, right? And if the pressure increases beyond a certain value, then flow separation takes place due to adverse pressure gradient. And this flow separation is absolutely not desirable because it deteriorates the compressor performance massively. So pressure ratio actually is restricted in a way so that the flow separation is avoided. So in compressor, as the flow passes through, the, the pressure increases. Right, and if pressure increases beyond a certain value, then flow separation takes place due to adverse pressure gradient. This flow separation deteriorates the compressor performance. And hence should be avoided. So the pressure ratio in one stage of jet engine compressor is limited by the pressure gradient induced separation in that stage, flow separation in that stage. So the pressure ratio is restricted in a way so that the flow separation is avoided. Okay. Next question. The thermodynamic cycle on which the jet engine operates. So the thermodynamic cycle on which the jet engine operates is an open Brayton cycle. Now, if we see the TS diagram of the the thermodynamic cycle for a jet engine, this will be something like this. Something like this, right? So this 1 to 2 denotes the compression, 2 to 3 compression in a which takes place in a compressor primarily. 2 to 3 is combustion chamber, 3 to 4 is the turbine where the flow expands, and then 4 to 1 is the exhaust nozzle where the flow is exhausted in atmosphere. So this 1 to 2 is compression, which is ideally isentropic. Then 2 to 3 is heat addition in combustion chamber. So heat is being added in this part, combustion chamber, and this is ideally isobaric, means the heat addition takes place in a constant pressure. And 3 to 4 is flow expansion in turbine. expansion in turbine, which is again ideally isentropic. And 4 to 1 is expansion through nozzle. And this heat rejection takes place in this process also, in this part 4 to 1. Heat ejection. Okay, so this is the TS diagram of an ideal jet engine. I mean, ideal process. But in reality, this compression in 1 to 2 will not, or expansion in 3 to 4 will not take place in isentropic condition. There will be losses. Also, 2 to 3, the combustion chamber there, that will not be taking place in constant pressure, because pressure will drop because of the losses. But for ideal condition, this is the TS diagram, and the answer is open Brayton cycle. So C is the correct option. The next question: propulsion efficiency of a jet engine is which of the following? So propulsion efficiency of a jet engine is, it has a formula. A jet engine is given by the following equation. It is the ratio of thrust power and propulsive power. Now, propulsive power is basically the net increase in the energy of working fluid between inlet and exit of the engine. Is the net increase in energy of the working fluid between inlet and exit of engine. Right, and this is given as dot 1 plus F Cj, which is the exhaust velocity, square by 2 minus Ci square by 2. Ci is the inlet velocity. Right, so Ma dot is the mass flow rate through the engine. Cj is the, so Ma dot is basically the air flow rate through the engine, and Cj is the exhaust velocity, Ci is inlet velocity, and F is the ratio of well flow rate and air flow rate. Okay, so propulsive power formula is this. So if we see the expression of this propulsive efficiency or propulsion efficiency, we can see that it is directly proportional to thrust power and inversely proportional to this Ma dot, right? So this will be the answer, directly proportional to thrust power and inversely proportional to the air mass flow rate. Next question. A turbojet powered aircraft is flying at Mach number 0.8 at an altitude of 10 km. The inlet and exit areas of the engine are 0.7 meter square and 0.4 meter square respectively. The exhaust gases have velocity of 500 meter per second and pressure of 60 kilopascal. The free stream pressure, density, and sound speed of sound are this respectively, and then what will be the thrust of the engine. Okay, so just draw a schematic of the engine. So this is the exhaust area, I mean exit area, this is the inlet area. Must wait. This is the force acting in the exit area, and this is the force acting on the inlet area. Right, PA is the atmospheric pressure. Now the given information in the question are: inlet area is 0.7 meters square, exit area is 0.4 meters square, inlet velocity, sorry, exhaust velocity is 500 meter per second. Exhaust pressure is 60 kilopascal. Free stream pressure is 26.5 kilopascal. Free stream density is 0.413 kg per meter cube, and speed of sound is 299.5 meter per second. And the engine is flying at Mach number 0.8. It's for the thrust of a jet engine is given by the thrust equation, which is T equal to m dot ue minus ui plus ae p minus pa. So pa is atmospheric pressure, which is equal to free stream pressure, right? So this is the momentum thrust. This part is known as momentum thrust, and this part is known as pressure thrust. And usually if the velocity of the engine is not very high, then in that case this pressure thrust part is ignored and only this part is considered for thrust. But when the velocity is very high, then this pressure thrust will also have contribution in the thrust produced by the engine. So m dot, this UE is given, AE, PE, PE, all these terms also given. So we have to find out m dot and UI. So m dot is the mass flow rate through the engine, which is nothing but rho infinity inlet area and UI. And Mach number is given as 0.8 at which the engine is flying, which is again UI divided by speed of sound. So from this we get UI as into 299.5 meter per second, which will come something around 239.6 meter per second. So if we just substitute rho infinity AI and UI value, we'll get m dot value. Now if we substitute all this value in the thrust equation, that will so 0.413 multiplied by AI multiplied by UI multiplied by exhaust velocity, which is 500, minus inlet velocity, which is 239.6, plus exit area. Exit area is 0.4 meter square, multiplied by PE. PE is 60 kilopascal minus PI. PI is P infinity, which is 26.5. These are kilopascal, so this will be multiplied by 10 to the power 3 to get them in Pascal. Now, if we just calculate this will come 31437 Newton, which is equal to 31.437 kilonewton thrust. So this is the answer. Moving on to the next question. A jet engine is operating at Mach number 0.8 at an altitude of 10 kilometers. The efficiency of the air intake is 0.8, and the compressor is 0.87. The total temperature at the exit of the air intake and the compressor respectively are these. So we have to find out the total temperature at the exit of air intake and compressor. And these are the values which are given: ambient pressure, ambient temperature, and gas constant. And PRC is the pressure ratio across compressor. So if we draw the TS diagram of inlet and compressor, so this one denotes the entry of the engine, and 1 to 2, this process denotes the flow through the engine inlet. And 2 to 3 is denotes the flow through compressor. And this 3s point denotes the isentropic condition, same as 2s, 0 to s, which denotes the isentropic condition. So 1 to 2s, 1 to 2s is the flow through inlet when the flow is isentropic, and 2 to 3s also is the flow through compression in isentropic condition, and this point denotes the real condition. So 1 to 2 is the flow through inlet in real condition, and 2 to 3 is also flow through compressor in real condition. Now it's given that the efficiency of the air intake is 0.8 and efficiency of the compressor is 0.87, and ambient pressure is given as 26.5 kilopascal. Ambient temperature is given as 223.3 Kelvin, and Mach number at which the engine is flying is 0.8, and we are asked to find out the total temperature at the exit of the inlet, which is TO2, and total temperature at the exit of the compressor, which is TO3. Now inside the intake of the engine, total temperature remains constant. Now, since total temperature remains constant inside the inlet, so total temperature at the entry of the inlet and total temperature at the exit of the inlet will remain same. So TO2 is nothing but the total temperature at the entry of the inlet, which is TO infinity. So TO infinity and we know that the ratio of total temperature and static temperature is given as 1 plus gamma minus 1 by 2 m square. Now T infinity and m gamma, all these values are given. So if we just substitute these values, we'll get the TO infinity. So gamma is 1.4, gamma minus will be 0.4 divided by its 0.2 multiplied by m square. M is 0.8 square Kelvin. So this will come something around 250 1.8 Kelvin. So TO infinity equal to TO2 equal to 251.8 Kelvin. Now the second part, that is TO3, which is the total temperature at the exit of the compressor. Now for compressor, the compressor efficiency is given by TO3s minus TO2 divided by TO3 minus TO2. So if we take common TO2 from numerator and denominator, so this both get cancelled, and this TO3 is divided by TO2. But this can be written in terms of the pressure ratio from the isentropic pressure relation. So TO3s by TO2 can be written as PO3 by PO2 to the power gamma minus 1 by gamma minus 1 divided by TO3 by TO2 minus 1. Now this PO3 by PO2 is the pressure ratio across compressor, so which is given by TRC, is PO3 by PO2. So this value is given, which is 8. So this is 8 to the power 0.4 divided by 1.4 minus 1 PO3 by PO2 minus 1. And this ITAS, the efficiency of the compressor is given as 0.87. So if we just solve this, and TO2 is known to us, which is 251.8. So if we just solve this, we'll get TO3, which will come something around 486.8 Kelvin. So TO3 is 486.8 Kelvin and TO2 is 251.8 Kelvin. So this will be the correct answer, option C. Next question. A rocket engine is tested on a test bed under ideal condition of fully expanded jet. The exhaust velocity is 2 km per second through a nozzle of area of 2.5 meters square. The mass flow rate is 200 kg per second. The specific impulse of the propellant and thrust produced respectively are. So to find out the specific impulse of the propellant and the thrust developed. Okay. So the given information, the exhaust velocity is 2 km per second. The exhaust area is 2.5 meters square. The mass flow rate is 200 kg per second. We need to find out the specific impulse and we need to find out the thrust of the produced by the rocket. Now thrust produced by rocket is given by m dot ue. M dot is the mass flow rate, exhaust mass flow rate, or mass flow rate going through the exhaust nozzle, and then P E minus PA AE. Now since the nozzle is fully expanded, so this term PE will be equal to PA Okay, PE is the pressure at the exit of the nozzle. PA is the ambient pressure. AE is the area of the exit of the nozzle. Now, since fully expanded jet, so PE will be equal to PA, hence this term will be 0. So T thrust produced by the rocket will be simply m dot UE. Now m dot value is given and UE is given, so you can get T as 200 multiplied by 2 into 10 to the power. This is 2 km per second, so that will be 2000 meter per second. So this Newton, which is 400 kilonewton. So T is equal to 400 kilonewton. Now we have to find out the specific impulse of the propellant. So specific impulse of the propellant, ISP, will be equal to T by m dot G. Right. So T value is this, and mass flow rate is 200 and G is 9.81. So this will come something around 203.87 second. So this is the correct answer, B. Next question. Consider a flow through an expansion corner for which the at the following conditions, which is M1 is 2, P1 1 atmosphere, T1 is 28 Kelvin, around a sharp expansion corner, theta 20 degree, as shown below. The Prandtl-Meyer function nu is given as function of Mach number by the following expression, and assume air to be calorically perfect with gamma 1.4. The Mach number M2 downstream of the expansion corner is approximately which of the following. So a flow at Mach number 2 is passing through an expansion corner with a deflection angle of theta, and you have to find out the Mach number at downstream of the expansion wave, which is M2. Right. So the given conditions, given informations, that is M1 is 2, P1 is 1 atmosphere, T1 is 28 Kelvin, and theta is 20 degree deflection angle. Now we know that for supersonic flow across expansion wave, theta will be equal to nu of M2 minus nu M1, right? For across expansion wave, minus nu M1. Now this nu M will be the formula of nu M is given, right? So nu theta is given. Now nu M1 is okay. So nu M is given as gamma minus 1 tan inverse of gamma plus 1 m square minus 1 tan inverse of m square minus 1. Now for nu M1, this will be gamma plus 1, which is 1.4 plus 1, that is 2.4, divided by gamma minus 1, that is 0.4, gamma equal to 1.4. Tan inverse of gamma minus 1.4 by 2.4. M1 means M1 square minus 1 minus tan inverse of M1 square minus 1. Now M1 is given as 2. Right, so if we just substitute the value of M1 here, eta of M1 will come as 26.38 degree. Now from this expression, we know that, I mean, theta is given as 20 degree. So from this expression, we can write that 20 degree equal to nu M2 minus nu M1, which is 26.38 degree. So from that we will get nu M2 as 46.38 degree. Now from this expression again, if we substitute the value of nu M2, that is 46.38, and the value of gamma, we'll get an expression. So just substituting value of nu M2 and gamma, we'll get this expression. It is 46.38 will be equal to 2.4 by 0.4 tan inverse of 0.4 by 2.4 M2 square minus 1 minus tan inverse of M2 square minus 1. Now for flow across an expansion wave, Mach number always increases. So M2 will always be greater than M1. Let's now flow across expansion wave. Mach number increases. So M2 will be greater than M1. Now M1 is 2, so only the options which satisfy M2 greater than M1 is these two options, C and D. So we have to do a trial and error with both of this value of M2 by substituting that in this expression to see which one satisfies this expression actually. So we have the so I'm also option given the value of M2 which satisfy these conditions are M2 is 2.83 or M2 is 3.14. Now if we just substitute value of this M2 in the right hand side of this expression, we'll see that M2 of 2.83 actually satisfies this expression. That is, if we substitute M2 of 2.83 in the RHS of this equation, that will be equal to 46.38, which is the LHS. So trial and error with these two value of M2 can get that M2 equal to 2.83 satisfies the above expression. So M2 2.83 is the correct answer. Next question. Consider an invisible adiabatic flow of air at free stream Mach number 2 across a compression corner theta 20 as shown. The free stream total enthalpy is 810 kilojoule per kg. Assume that the air is calorically perfect with gamma 1.4 or 287 joule per kg Kelvin. So what will be the shock angle beta and the total temperature at point P? Okay, So if we just, okay, the given expression with the given information that the free stream Mach number is 2 and deflection angle theta is 20 degree. So this is the flow downstream of the oblique shock, and the shock angle is beta. This is U1, right? And this U1 will have two component. One is U1 sine beta, which is perpendicular to this shock wave, oblique shock wave, and another one is U1 cos beta, which is parallel to the oblique shock wave. So this is U1 sine beta, and this is U1 cos beta. Now for oblique shock to exist, this U1 sine beta, this component of the upstream velocity is perpendicular to the oblique shock. So this oblique shock to exist, this U1 sine beta has to be more than the sound speed of sound. Okay, so the normal velocity would be greater than speed of sound for oblique shock to exist. Right. So this U1 sine beta should be greater than speed of sound, which means U1 by A1 sine beta should be greater than 1, which means M1 sine beta should be greater than 1, and M1 is the free stream Mach number of the flow, which is given as 2. So sine beta will be greater than 1 by M1, or greater than half, which means beta is greater than sine inverse of half, or beta is greater than 30 degree. So option D is the correct answer. Now going to the second part of the question, the total temperature at point P. Now total temperature across an oblique shock remains constant since there is no heat addition or heat retraction. So total temperature at downstream of the oblique shock and the upstream of the oblique shock will remain same. So if this part is 1 and this part is noted by 2, so total temperature oblique shock remains constant since there is no heat addition or heat retraction. So TO2 will be equal to TO1, that is the total temperature at downstream of the oblique shock will remain same as upstream of the oblique shock. So and total temperature as point P is TO2 TO1. Now TO1 is the total enthalpy, free stream enthalpy, divided by Cp. Right now, Cp is given as gamma R by gamma minus 1. Gamma and R value are given. So if we substitute gamma and R value, to 87, this will be this will come as 1004.5 joule per kg Kelvin. Right. Now this is the value of Cp. So HO infinity, that is total enthalpy at upstream of the oblique sock, is given as 810 kilojoule. So this will be 810 into 10 to the power 3 at this joule divided by 1004.5 Kelvin. So if we just calculate this, we will get 806.37 Kelvin. It is the total temperature at both upstream and downstream of the oblique sock. So total temperature at point P is this 806.37. Option A. So that's all. These were the questions of gas dynamics and propulsion part in K 2011, and we have solved all the questions. Thank you.